just to give some training also for you, for students. Okay, I came from Turku in Finland, which is located at nice archipelago. You can see it on this picture. And I'm working in the Department of Physics and Astronomy, University of Turku. This is one of the oldest universities in Finland. Here are the members of my group, experimental side and theoretical side. And some of these people, actually, my younger colleagues, have been already delivering talks here at these conferences. Jarno Järvinen was exactly 1 year ago talking about dynamic nuclear polarization. Now the topic of my talk is a little bit exotic because it's quite far from all what I have heard yesterday, and it belongs really to fundamental quantum physics. And if you ask me about motivation, here is the outline. While you are reading, I will explain that if we think about motivation, and when I try to answer what is the main goal, I remember now one of the fifth criterion, which was announced here, that бесполезность. Probably we quite well satisfy this criterion because this is purely fundamental research. It concerns some fundamental physics, quantum physics, at quite extreme conditions, which may be quite exotic for you. And therefore, since it is rather exotic, I'll try to do it so that it will be understandable for non-experts. But if you feel that you don't understand completely, you may interrupt me with questions. Let's agree so. So I will be talking about quantum gases. I will define what it is, explain what does it mean, and what are the properties. Then I will explain how the spin waves appear in quantum gases and what are specific features. Then I will explain our experiment, how it is designed, what are the main features and criteria. Then show the spectral spin waves, and then explain how the spin waves or magnons can be trapped, and finally show that we observe some phenomenon which is similar to Bose-Einstein condensation of real atoms. Now we see it with quasi-particles. This work is published here quite recently. So now if we think what are the spin waves, perhaps most of you have heard or studied that spin waves are known in ferromagnets. There we have, it is basically a solid where all nuclei or atoms are fixed rigidly, and they appear due to exchange interaction of their electrons. And nothing is actually moving there. So we have spins which are polarized or aligned. It can be ferromagnetic, it can be antiferromagnetic. And then we create some perturbation. We tilt one of the spins. Because of the interactions, like in a string, it causes spin flips with the other one, and this kind of perturbation may propagate, we get spin waves. But what happens if we consider a gas? Well, there the atoms are moving, and on the average they are located quite far away from each other. How can there appear spin waves? It turns out that they can appear and under special conditions which define quantum gas. So let's consider a gas which is first warm, let's say at room temperature, a gas of atoms, and then we start to cool it. Of course, at room temperature, the collisions of the atoms, they can be considered like collisions of the hardballs. You know this quite well. When we start to cool our gas, the atoms start to delocalize. They are better described like spin packets or waves. And the delocalization length, which is called thermal de Broglie wavelength, probably also that you should know, starts to increase. And lower temperature, this thermal de Broglie wavelength is becoming substantially larger than this hardcore radius of interaction, which was at room temperature when they were colliding. So it may substantially exceed this hardcore radius. At low temperatures, this is defined, and this is called the S-wave scattering length. Finally, if we go even further, even colder, perhaps you know what happens with such gas of atoms. They undergo phase transition to Bose-Einstein condensate, which was first predicted, by the way, for the light particles, for photons, by Bose, and then generalized by Einstein, and now first time it was reached in 95 in vapors of alkalis. In 98 it was reached in hydrogen, this phenomenon, in atomic hydrogen. And now it's a routine thing. It's a large, huge community who study people, atomic physicists who study Bose-Einstein condensates. I will not concern any Bose-Einstein condensate. I will talk about so-called non-degenerate gas. In Bose-Einstein condensate, thermal de Broglie wavelengths actually is becoming so large that it exceeds mean interatomic distance. So that all time, whenever they are with respect to each other, the atoms are not distinguishable anymore and they are described by the same wave function. I will not go to this regime. I will concern this regime, which is called quantum gas regime. What is specific here? When we had classical collisions, to get the collisions, the atom should approach to the distance of this AS, the hard core radius. But when the thermal de Broglie wavelength is large, they may approach to the distance of the thermal de Broglie wavelength. In this case, they do not scatter elastically. They don't exchange momentum. But since they are so close, so their wave packets are indistinguishable, they can exchange any property, what they are different. And therefore, they pass through each other. And for example, if they have slightly different spin, they may exchange this spin. So they may undergo spin exchange in collisions, in rather short encounters, compared with, and this is the difference from the ferromagnets. So in our case, I will specifically describe the system of atomic hydrogen. And of course, to satisfy this transition, because thermal de Broglie wavelength is inversely proportional to the square root of the mass and temperature, of course it's better to work with lightest gases. They have largest thermal de Broglie wavelength. And therefore, for example, atomic hydrogen is the best candidate. In our case, these parameters of the thermal de Broglie wavelength, its ratio to the scattering length, is of the order of 30 to 50. So we are quite well in the quantum gas regime. In terms, if we compare thermal de Broglie wavelength with average distance, we see that the average distance is still larger, substantially larger. That's why we are not in the degenerate regime and we cannot talk about Bose-Einstein condensation in this system. Now what actually happens when we have such spin-changing collision? When two atoms approach to the distance of the thermal de Broglie wavelength, they interact, and this is isolated pair. If they have slightly different spin, due to interaction, they may exchange this spin. But the total spin must conserve, because this is isolated pair. Therefore, what they do, they rotate around their sum. So this kind of exchange in this collision, spin-changing collision, it leads to the spin rotation effect. So if we had Earth spins polarized and tilted one of them in collision with another spin, they both rotate a little bit. And then continue to travel with the same direction and velocity, because they don't change momentum. Therefore, if we create some perturbation in spin-polarized gas, this perturbation in multiple collisions, we need many collisions, will propagate. And this may lead to appearance of the spin waves. So basically, the spin waves are the waves of the transversal component of the magnetization, which we create in the spin-polarized gas by, for example, applying some resonance RF pulse or excitation. They can be traveling, these waves, and then superposition of traveling back and forth gives us standing wave, may give us standing wave. The theory is not quite trivial to derive the equation which describes this spin electron, or actually it doesn't matter in this case, but the spin waves in quantum gases. However, it was derived in a simplified equation. It looks like this in this form. So this is the equation for the transversal magnetization. It is expressed via the spin diffusion coefficient. This epsilon is the coefficient 1 or minus 1 for bosons or fermions. This mu is a special thing which defines the quality factor of the magnons. It's the ratio of the thermal de Broglie wavelength to the scattering length, which in the case of quantum gas is much larger than unity by definition. Then there is this gyromagnetic ratio, deviation of magnetic field from the average. This is delta B. And again, transversal magnetization. If you look carefully, this equation is exactly of the Schrödinger equation form. So it means that basically description of our magnons or our spin waves is similar to the behavior or description of real atoms in trapping potential, which can be done now with magnetic field. So the deviation of magnetic field work as magnetic potential. And this is the kinetic energy term with such effective mass now. And if we evaluate this effective mass, taking some realistic value of this quality factor mu lambda, we will obtain that actually the effective mass of magnons for atomic hydrogen is of the order of electron mass. It means that basically observation of such phenomenon like BEC would be easier for magnons. Now, what kind of gases we can consider, for which the spin waves were known and really in experiments people observed that? This is of course vapor of helium-3 or the solution of helium-3 and helium-4 in liquid form. Here epsilon is -1, gamma is negative for nuclear spin, and mu, the quality factor. Its sign depends actually on the details of the interaction. It can be negative or positive, it must be calculated, and it is different. So for helium-3 it is change in sign, and can be negative and then changes sign with temperature to positive. For proton spin of atomic hydrogen, it is +1 epsilon because a hydrogen is boson, gamma is positive, and mu turns out to be negative. What does it mean if mu is negative? It means that the potential energy minimum will be observed in the minimum of magnetic field. Situation is different for the H electron spin. Again, it is boson. Gamma is negative and large, 1,000 times larger than for proton. And mu is again negative. So we can see here that for hydrogen, looking on these equations, the minimum of potential energy will be located in the maximum of magnetic field. So hydrogen, in analogy with real cold atoms, where the BEC, for example, is studied, hydrogen spin waves, they are high field seekers. And this is different from most of the quantum gases where real BEC is observed. They are typically low field seekers. They are accumulated in traps in the minimum of magnetic field. But our magnons, what we will consider, they may be accumulated or trapped in maximum of magnetic field. And that's the difference, and this is rather good difference because it allows us to make many interesting things. Spin waves of atomic hydrogen for protons, for nuclear spins, were first observed in experiments of David Lee at Cornell University. That was the end of 80s. And in the NMR spectrum, they saw modulation of the spectrum with rather sharp features. Remarkable was the thing that they observed this phenomenon even in Knudsen regime. And this is in principle understandable. As I said to you, Knudsen regime defined as with respect to elastic collisions. But elastic collisions are bad for us. We need spin-changing collisions, which happen much more frequently. That's why we may not have elastic collisions. It means that the mean free path is much larger than the distance between the walls of the chamber. But we may have, on the other hand, quite many spin-changing collisions once the thermal de Broglie wavelength is large enough, if we are in quantum regime. So this just justifies this quantum gas approach and requirement for observation of the spin waves. For electron spins, there were many attempts, and only 7 years ago we managed to make an experiment where we first time observed, and I will now tell about it. But first I will tell you about atomic hydrogen. You know, and the word hydrogen has been used here, I guess, most of the other words in all the talks. But you were all talking about not free hydrogen. It's hydrogen bound in some molecules, at least in H2. And you were mostly talking about proton NMR of this hydrogen. I'm talking about isolated atoms, the gas composed of atoms, not molecules. And it is quite clear that this is metastable system. I would rather say it's extremely unstable system because the energy of combining two atoms into molecule extremely large compared with Zeeman energy. It's 55,000 Kelvin in temperature units. But Zeeman energy, depending on the field, in the field where we work, it's 6 Kelvin only. So whatever you do in collisions, these atoms will eventually like to join to molecule. And the only way to stabilize them is polarize electron spins. Then they can't combine to molecule. Okay, but then still, if we accumulate such gas of spin polarized atoms, how can we do them spin polarized? Just by brute force. Let's cool them to temperature below 1 Kelvin, and let's apply a field of few Tesla. As I said, in our field, the energy is 6 Kelvin. It means that if we work at 0.5 Kelvin, which is the temperatures of our experiment, the electron spins are extremely well polarized to a very high degree. But it turns out that in this gas, even if it is in contact with some container, with the walls, absorption energy of hydrogen is rather high. And the atoms will absorb on the walls of this container, and the density will be exponentially dependent on temperature. The lower the temperature, the higher is the density. And eventually, any magnetic perturbation would lead to the spin flip, and they will recombine. Therefore, hydrogen must be accumulated or kept or trapped in the container with smallest absorption energy. And it turned out that liquid helium has smallest interaction energy with anything, also with hydrogen. So the walls of the chamber must be covered by superfluid helium. At these temperatures, it is superfluid helium film. Okay, so now we accumulate such gas in a container with the walls covered by superfluid film, and we apply a magnetic field and cool, everything is cooled to temperatures below 1 Kelvin. Now let's recall what are the energy levels of hydrogen atom. Actually, why is hydrogen extremely good system for all magnetic resonance measurements? Because it's just classical two-spin system, electron and proton, and hyperfine interaction between them, which leads to 4 energy levels, probably also well known to you. I use adopted in atomic hydrogen research notations A, B, C, and D states, which are different by the projections of the electron and nuclear spins, and high field projections are good quantum numbers, and they quite well characterize the spin states. These 4 states, 2 of them are so-called pure states. They are just having pure projections here, A and D, but A and C are mixed states, where even in high field there is a small admixture of the, in C it is a admixture of A state, and in A it is a admixture of C state. This mixing factor is dependent on magnetic field. It's defined by the ratio of hyperfine interaction to, over the Zeeman energy. And in our field of 5 Tesla roughly, it's of the order of 10 to minus 5. So it's rather small, but it turns out that this small factor is sufficient for having a small probability of the other spin, electron spin direction. And in collisions of, for example, these A atoms with each other or with B, we have enhanced probability of recombination. Therefore, if you accumulate the gas of electron spin polarized, it means mixture of A and B, quite soon, because of recombination into molecules, this A state will burn. And we leave finally only with the state which is called doubly polarized atomic hydrogen gas. So this is the gas with which we will work and do experiments. Then it is doubly polarized, so there is no any admixture. One may think that it will not recombine. No, it turns out that in free body collisions, dipolar interaction may lead to the spin flip of one of the 3 and lead to recombination. Now we have 3 bodies, and this may happen even in the bulk, not on the surface. Because basically for recombination we need 3 bodies to satisfy conservation laws of energy and momentum. So main decay mechanism of our hydrogen gas, it is free body recombination, which is shown here, and which actually limits the lifetime of our samples depending on density from several hours to several minutes. Now about experiment. As I mentioned, we need magnetic field of 4.6 Tesla, which is a routine for superconductive magnet, but it should be, of course, good magnet with high homogeneity. We reach temperatures of 0.2, 0.5 Kelvin with the use of conventional, I don't explain what it is, but just a refrigerator, dilution refrigerator. And we have here our sample cell inside the magnet in the center. we have special dissociator where we split molecules to atoms, and then the certain spin orientation is pulled into the sample cell by the gradients of magnetic field. And the sample cell has a resonator, which is connected to the ESR spectrometer, and for this field, the resonance frequency of ESR is 128 gigahertz. This is quite exotic frequency. Unfortunately, we must go to so high frequencies, and we can't use commercial devices because of this high frequency. So we had to build our own spectrometer, but owing to a possibility of having cryogenic environment, we built it at cold. So millimeter wave bridge of the spectrometer is located at 1.5 Kelvin temperature. Therefore, it allows a strong reduction of noise. And basically, we reach extremely high sensitivity of the order of 10 to 7 spins at extremely low excitation power. Why we need a low excitation power? Because you understand that once we work with spin polarized gas, which will recombine to molecules being depolarized, ESR excitation is just a source of depolarization. So any spin flip will kick out this atom from the game. It will just leave, recombine. And now the details of the sample cell. The core thing here is that the resonator is the open Fabry-Perot type. It has semispherical mirror and flat mirror. So these are two mirrors. This is a picture of the millimeter wave field inside. The wavelength is of the order of 2.4 millimeters at this frequency, so the size is quite compact. And now, of course, we could just fill it with the gas, all cavity. But that wouldn't work due to several reasons. First of all, it turns out that at the densities what we need for reaching spin waves, and the density should be of the order of 10 to 17 atoms per cubic centimeter, or even higher, we reach actually maximum 3 times 10 to 18th. By the way, it is quite amazing that one may get such density, which is 1/10 of the gas density in this room. But this gas can be cooled to that low temperature. And this is also the feature of atomic hydrogen gas. It's the only gas which will remain a gas and not liquefy or solidify at absolute zero. So this wouldn't work due to several reasons. One of them, if we fill the whole cavity by a gas, the interaction or absorption of the energy in resonance, because of the high energy of the quantum in this field at frequency, would be so large that we would simply destroy the cavity Q. The response of the cavity of the system would be completely nonlinear. That is bad. Second thing is that due to this recombination, three-body recombination, it's a lot of heat is released. As I said, in each recombination event, 55,000 Kelvin, just for these temperatures, very nice feature. So we need to remove recombination heat. And therefore, our region where we get this hydrogen gas, we need to cool it very well. Second thing is that with this geometry, just filling from the dissociator, sample cell, we cannot reach very high densities of what I said. We may reach maximum of 10 to 16th. So we need to find some way how to compress the gas. The solution was found, and one more requirement is that we cannot excite spin waves if we have homogeneous RF excitation. It's quite clear if we tilt all spins at the same time to the same angle, there will be no any spin waves. So we need inhomogeneous RF field. And the solution was found in this way. We just placed here our hydrogen volume, sample cell lower part, which is here, which is cylindrical mylar polyimide tube, 0.5 millimeter diameter, which goes into this container. And we control the volume of this container by a special U-tube system, which is based on the superleak. Quite specific for you and exotic. I try to explain what it is. So it is the tight piece of the tube packed with some powder, which may allow only the superfluid component of helium go through it. So applying heat to this part, we create a fountain pressure here. The superfluid goes here and raises the level here. So we can fill in this system with helium, this U-tube system, and heating this volume. We can lower helium in here down to the bottom and make it empty. Then from our hydrogen source, dissociator, we put hydrogen gas inside, fill all this volume, And then we start removing this heating. So the level here goes down and here it goes up. This way we make simple piston compression with the liquid helium of the gas by the factor of 1000, because this cross-section is much larger also. And from the 10 to 16th we may easily go above 10 to 18th. So this is the schematics, and now this is the sketch of how it looks like. Actually, in this YouTube system also we have one capacitor. It's a special place to capacitor plate to measure the level of helium here, which again due to special tunnel diode oscillator, which is located again at cold, allows extremely high resolution. We can measure here the changes of helium level with the sub-micrometer resolution with this device. So here is how it looks like, and one more feature here is that the microwave field from the cavity penetrates into this volume through a subcritical 0.4 millimeter hole in the plating. This is a gold plating with a 0.4 millimeter hole on it. And it is also sealed. From all this volume are sealed with respect to the vacuum outside. One more thing here is that the outer wall of this mylar tube or polyimide tube is cooled by separate stream of superfluid helium. This is needed just to remove the recombination heat, what I said. Looks rather complicated, and it took perhaps a couple of years for us to get it working, and finally we got it. So this is how it looks like. This is this opening here, this is the Kapton tube, this is in scale, all these pieces. This is the fill line, this is this volume where hydrogen is accumulated before compression, then it is compressed into this small tube. The wall thickness of this polyimide is 3 micrometers. And of course, it is flushed by superfluid helium to remove the recombination heat, and of course we needed to seal it. And when my student was making this whole system, and he used epoxy, this all gray stuff is epoxy, Stilcast 1266, quite well known in low temperature physics. I asked him to use as little epoxy as possible here, because one other feature of this construction is to avoid as much as we can any magnetic materials here. And I asked him, just put as little as you can. He made it, and it has got a super leak, so we couldn't work with it. Super leak means that at cooling it below 2 Kelvin, we got poor vacuum here. Helium was just going outside through this super leak. Okay, and then he made a second version in which he actually added more epoxy. And this is important. I will demonstrate you later why this is important. So here is our cylinder, the polyimide mylar tube. It's actually Kapton, the brand name. Here is our helium piston. Here is our microwave RF field, which has, we call it evanescent field, because it is really evanescent field from the Fabry-Perot cavity, which extends downwards by about 80 micrometers and folds down exponentially with going down from the hole coupling to the main cavity. And here in this direction it is Gaussian, its profile. What is specific about this epoxy, which finally he has put here with the thickness of about 0.5 millimeters, this, just to get reliable seal. It turned out that epoxy is slightly diamagnetic in these strong magnetic fields. And being diamagnetic, it has magnetization opposite to the magnetic field, which is, I directed it upwards. So in these regions inside the gas volume where we compress it, it creates some extra field. So the field is directed up. So we get maxima of magnetic field and field inhomogeneity due to this epoxy. And this turned out to be bad at first, as we thought, but then we realized that on the other hand it gave us a lot of interesting things and new experiments. And so I will now consider in this cylindrical volume where we compress our gas, excite the ESR and spin waves by this evanescent field, RF field of 128 gigahertz. This volume is surrounded by weakly magnetized diamagnetic epoxy, which creates extra field of about 0.3 Gauss here. In the field of 46 kilogauss, you can imagine how small actually in homogeneity it is, but it turns out to be important. And I will consider two types of experiments. We may, on our wish, stop our compression at any level. So we can move this piston, leave it somewhere here, move it here, here, or more. If we leave it far enough from the top, the sample will simply decay due to recombination, so we get maximum density. In the beginning, after stopping the compression, we get maximum density, and then due to recombination, density decreases, helium level slightly goes up, because hydrogen, of course, creates also some pressure as a gas. On the other hand, we can compress it more, so much that it goes this level somewhere quite close here, and hydrogen starts again recombine, decrease density and pressure, but then at some stage it's becoming profitable for the whole volume from cylindrical shape to get into the bubble, just to decrease surface tension, because helium also has some certain surface tension. So in this case, we finally get a bubble where the pressure of hydrogen is balanced by the surface pressure of this helium, surface tension of helium. In this case, the smaller is the size of the bubble, the higher is the pressure, and the higher is the density. So the difference between these two types of experiments is that here we have maximum density in the beginning, but here we have maximum density in the end, when the bubble is smallest. And we can actually control, I will show you, these bubbles, how does it behave. We can see its spectra down to diameter of about 20 micrometers. So first spectra, what we see. Of course, in our hands is also one more feature. We can apply axial gradient of magnetic field. We have special anti-Helmholtz system of gradient coolers, which can apply rather large gradients of the order of 30 Gauss per millimeter. So the spectra what we see, we are plotted here with respect to the gradient. So in different gradient, you see we change it, it goes through 0, and then changes sign. What we see here, we see main ESR absorption peak. And at small density, believe me, I will show the spectra. This strange looking feature goes to just as normal single peak, nothing special. So this is normal ESR peak. But already here you can see that it is modulated. And these are these spin waves with which we were looking. I will discuss it in more details. But now what is more interesting that even in zero field, we saw in zero gradient, we saw that there is, in addition to main ESR peak, some special peak, which actually moved more far away if we increase negative gradient. But then if we change the sign of the gradient, one would think that this peak is due to the, for example, we may have two maxima of our RF field. In this region somewhere here, we have our evanescent field, and for example, due to some reasons, we have another maximum of magnetic field. And therefore, we would see two peaks in gradient. But if we change the sign of the gradients, perhaps all you understand that the relative positions of these two peaks should be mirror. So if we now change the sign of the gradient, we go through 0 here. This peak approaches really our main ESR peak, but then if we change the sign, we see no any peak, nothing. And this can be interpreted, cannot be therefore interpreted as a second RF maximum. And the only reason for this peak is that here, due to this magnetized epoxy and maximum of magnetic field, we get actually a trap for Magnons. And this signal here is nothing else but the signal of trapped Magnons. And this was very interesting. This was a big puzzle for us and took a while to understand why is it so, why this peak exists, and why does it move only on one side. Reversal of the gradient doesn't move it on the other side here. It doesn't. We don't see it here. Okay, so we then realized that we really indeed see, first of all, some spin wave modes which modulate our main ESR peak. And we see also peak from the trapped Magnons in occasionally created trap by this epoxy here. It is saddle shape magnetic field maximum close. Maximum is near the wall, which like it would be from the coil. Next, what we studied, we applied very large gradients of magnetic fields so that this inhomogeneity due to Steilkast can be neglected. So we applied much stronger gradient of the field. What we saw in our ESR lines, here the lines are recorded by continuous wave method. I didn't say when I described the spectrometer, we have spectrometer which can be operated in both modes. So continuous wave when we fix the frequency and sweep magnetic field through the resonance. And it can operate also in a pulsed mode. When we apply a short pulse resonant with our field, and the length of the pulse defines how broad spectral region it covers, how broad region of the line it covers, of course. It can be soft or hard pulse, as what you should know what does it mean. These are CW spectra where we sweep magnetic field. So here it's actually calculated into frequency. And we verified that if we apply broad enough excitation, pulsed and CW spectra exactly coincide with each other as it should be, except special cases which I will tell later. So basically there is no surprise, we could record this by pulsed ESR, and we did it also as well. What we can see here at low densities, density is increasing from bottom to the top. So we start from the top with highest density. This is the compression where we stopped here, no any bubble. The sample just decays to smaller density, and in the end we have it rather small, and all modulation features disappear. These are indeed electron spin waves, and now if we just try to solve it, this Schrödinger equation, what I showed, in this simple case of linear magnetic field, linear potential energy, the solutions of the Schrödinger equation can be found analytically, no problems. These are combinations of Bessel functions, products of Bessel functions and Airy functions. So here is this picture of the potential, which now increasing downwards, and we have our excitation here in this region. So it means that what we see here, we see trapped magnons. But now they are trapped near the top, not in this Steichast created trap. And when we sweep magnetic field, we just make in resonance different regions here. We scan from top to bottom, let's say, and we excite different amount of modes. They overlap with each other, and therefore we see quite complicated picture. We tried to simulate this spectrum numerically, and we basically got exactly same pictures what we see in the experiment. So that was explained, no surprises. Then we reverse the gradient. Now the magnetic field is increasing downwards, so that the potential energy is decreasing downwards. Now we cannot have any trap here. But we see strong, very strong, this is perhaps most peculiar feature due to the spin waves. So again, at small density here, we don't see any modulations. Just a single peak broadened by inhomogeneity of magnetic field in this volume in our excitation region. Normal ESR signal in inhomogeneously broadened line. But then few more peaks appear at higher densities. What are these magnons now here? Scanning again magnetic field through this excitation region, because we excite spins only here, we launch different spin waves in two different directions. One goes down and the other one goes up. It is reflected from the boundary for this helium, liquid helium wall is ideal reflective boundary for spin waves. And then this wave which was launched down is interfering with the wave which reflected from the top. Therefore, we see interference of these two waves, traveling waves. One was launched down, the other one reflected up and reflected and again going down. So these are now traveling waves. And we see their spectra. Again, it can be described analytically, and here we get quite well coincidence of our theoretical description based on this transversal magnetization, these Bessel and Airy functions, with the observed spectra. Again, in principle, interesting, but since it is explained, no surprise and no interesting anymore. Then I turn to the spectrum which we actually observed first, when we have not applied any gradient, and I showed it here. In this gradient picture, this was done, these all spectra were recorded for modest, not very high density of hydrogen gas. This is zero gradient, nothing applied, and as I explained this peak, we clarified that it comes from these trapped magnons. Okay, but let's study in detail, how does this spectrum in this picture, how does it behave with respect to hydrogen density? So now we see that this is the spectrum at low density, density is increasing, this peak remains, but then suddenly on top of it, some very sharp and narrow feature appears, which has somewhat different phase from the main ESR signal. And that was a big surprise. We could not understand and realize what it is. We realized that this is in general the peak of trapped magnons, But at the bottom, at the lowest energy here, appears very sharp feature. So it more or less coincides with the position of the ground state in this trap. And we see that increasing hydrogen density, suddenly the population, the signal from this ground state, strongly increases. We tried to analyze numerically and find solution of these Schrödinger equations for this geometry where we do not apply any gradient, where we have this trap and trapped magnons. So we tried to find the modes of these magnons, and we found them. They look like this. Several modes are plotted here. So this is the transversal magnetization map. And we found also the energy spacing between this mode. It's placed here. These are just the energies calculated in magnetic field. You can see that the separation between modes is rather small. It's of the order of several milligauss. So basically, when we look on this peak here, it's just a superposition of many, many closely located by few milligauss modes inside this trap. And no surprise that we cannot more or less separate them. But on the other hand, as I showed, we can see that very strong signal emerges at high enough hydrogen density. So this is actually an interesting case of interesting situation for trapped particles or for trapped gases, now the quasi-particles, the magnons, when we have a box and inside it, somewhere in this region, we have some trapping potential which is not exactly parabolic like on this picture. But there are modes and states here. These just Magnon modes what we observe. So once we go above this, we go to continuum of the modes which are much less separated with much smaller frequency difference, which would be just magnons trapped in the box, which I showed to you before, launched up and down and in the other value of the gradient. Now I turn to the second type of experiment, which I mentioned in the beginning, that we may have cylindrical geometry. We stop compression early enough so that the bubble, the sample, the gas, remains cylindrical. It slightly changes its height, but it just decays to smaller density and leaves empty cylinder here, basically. But if we compress strong enough, it eventually evolves to the bubble. And this bubble is self-compressed by the surface tension. So this is different type of experiment, and higher densities can be reached here. And now with this bubble, we avoid, it's not overlapping with this Stijlkast trap. But on the other hand, of course, we can play with magnetic field gradients, applying gradient on our wish by this anti-Helmholtz coil. So we can organize a trap ourselves. Depending on the sign of the gradient, we can make it either near the upper end or lower end of the bubble. The lifetime of this bubble is of the order of 70 seconds usually, so it's rather short-living. So basically, to detect all dynamics here, what happens, we needed to use mostly the pulsed ESR. The pulsed ESR allowed sampling the spectrum every second, 1 second. Temperature in the bubble also increases due to recombination. We estimated that it can go nearly up to 800 millikelvin, but this is still low enough. Again, with the bubble, we can consider two regions, two types of experiment or two regimes. Large enough bubble, which is larger than the size of our RF evanescent field, larger than this 80 micrometers. This is 0.5 millimeters, so we can easily have such bubble. When it evolves to a smaller one, self-compresses, it can go much smaller, and even much smaller than this compression region. Now, in this case, all regions of the bubble are excited. On all gas, on all volume, we may act with our RF field. In this case, we act only on the upper part. And this final stage, when the bubble is substantially smaller or smaller than this evanescent region, it lasts 7 or 8 seconds. It's rather short, but most interesting things just happen in this stage, and thanks to our pulsed ESR, actually, we can even get 0.5 spectra per seconds per spectrum. We can still see and record dynamics of this bubble, and we can see the smallest bubbles which are having diameter of about 20 micrometers. So now this last stage of the bubble, it's not this 7 seconds, it's a little bit longer before. So this is a case when we apply positive magnetic field gradient. It means that magnetic field is increasing upwards, and the minimum of the potential energy, which is reached in maximum magnetic field, is reached near the bottom of the bubble. It's here. So we have compressing bubble, self-compressing, always having our largest magnetic field and the trap bottom here at the top. So here is our ESR signal, what we see from top to bottom time evolves. So this is the largest size of the bubble, beginning of the experiment, this is the end. So we see some magnons again unresolved, some maybe weak peak here. Suddenly in the end of the bubble compression, in this region corresponding to this minimum emerges very strong peak, which again corresponds to the lowest energy mode, to the bottom of the trap. Here it is plotted the density, which we simulate, we cannot measure it. As a function of time during this decade, this time scale corresponds more or less to this spectra. So you see, finally we can reach something like 3 times 10 to 18th density. And here is the size of the bubble. This is the scale is here. So it goes to roughly 20 micrometer size, the last points. And here is the temperature, which is more or less linearly in this approximation, what we used, growing to something like 800 millikelvin. So if we make this two-dimensional picture, it's more clearly seen here that really in the end something special happens in this ground state. Its occupation is strongly enhanced. Now we reverse the magnetic field gradient. So now the field is increasing downwards. And since the bubble is squeezing now, compressing itself, the bottom of the trap, or the maximum of magnetic field, it's now moving in time. And since we have a gradient, this should be seen in the spectrum. So the position of this mode, or of this line, of this peak, should also move, because it is in the gradient. So what we now observe, we see some spin wave modes here. Again, the sample evolves, bubble decreases, and then in the end, again, we see large peak emerging, which is growing in time, closer to the end of the life of this bubble. But its position is now moving in accordance with the position of the lower end of this bubble. Again, this proves that this strong peak corresponds to the lowest ground energy state of the magnons, or these electron spin waves in this trap. Now, one more feature which I already said is that when we look to this continuous wave or pulsed spectra, it doesn't matter, we can see main ESR peak, and this feature from the ground state of the trapped magnons, it has a different phase. How can it be? Well, in principle, it is explained because the distance from the region where we have maximum of our evanescent field from the center of this cylinder, it's half cylinder now, and this is the trap. And this is the trap bottom. This is roughly quarter of the wavelength. So for the wave to travel from here to here, you get pi/2 phase shift, which is quite well confirmed here. So it is another evidence that this signal originates from this region. Now I switch to the pulsed ESR mode, pulsed spectra. So this is continuous wave spectrum, which I already showed. This is the main ESR peak, and this is this feature from the ground state magnons, which is having a phase shift. But now the difference of pulsed ESR, which you of course know, is that making long enough pulse and narrow in the spectral range, in the spectral domain, we can selectively excite different regions of the inhomogeneously broadened line. So for example, this line is inhomogeneously broadened. This corresponds to our evanescent region here. And this region, this peak, corresponds to this region. And actually, one more thing now to recall is that this field is exponentially decaying if we go downwards. So the intensity of our RF excitation, our field here, is 20 times larger than here. So we have much stronger excitation here, but we still see quite good peak. Now with the pulsed ESR, we can selectively excite our atoms here or here. If we just use long enough pulse, here is the shape of the spectral shape in the spectral domain, the shape of our pulse. We used Gaussian-shaped pulses. So we tune, for example, the center of this shaped pulse to the position of the evanescent region, this maximum of the main ESR signal, and we get such spectrum. Even though we excite atoms only here, we do not have excitation here in spectral domain, and intensity here is 20 times smaller. We still get substantial signal. We can see signal of these trapped magnons. But now what happens if we just tune our excitation to this trap bottom, to this position. So we move our excitation pulse here. We see extremely strong pulse from trapped magnons and no any ESR signal from the normal gas here. And this is even because, even under the conditions when the intensity of the field here is 20 times larger than here. So this shows how strong is this excitation of these trapped magnons. How big signal they bring from here, very far away from the, our excitation field, to our cavity after all, and we can see it. Now if we look on the free induction decay in time domain, this is how it looks like. Well, in principle, what we would expect that you should guess, and basically any student here should answer, if I just make very wide excitation pulse and I cover all this spectrum by my excitation, what should I see in time domain here? If I make Fourier transform, I will see the same. But now in time domain, what I should see? I should see superposition of two decaying exponents. One is rather short decaying with short decay time from this broad signal. And the other one from this rather narrow one. And of course they have some phase shift. But what we see here, and these two overlapping exponents would give just decaying monotonously signal, free induction decay. But what we see here, we see a short part, really. This decays, this main ESR signal, it rapidly is destroyed. We are in some inhomogeneous field. But then suddenly, signal reappears. And it is this narrow feature. So this tells us that this narrow feature, this excitation of magnons, does not appear immediately after the pulse. They need some time to accumulate there. Now if we look and compare these free induction decays before this critical point when this narrow and sharp feature emerges, and after, we see the difference. So here is before, the signal before the critical point. Nothing special. Again, fast decaying exponent and slow decaying. But when we go through the critical point, and after the critical point, we see the growing part, and if we decompose it to two oscillating signals, we can really see that there is a component, this red one, which grows in time. And probably starts to grow just after, at the beginning of the pulse. The pulse is here, of course. We don't have basically any delay time here because in these frequencies the bringing of the cavity is very small and our excitation power is also very small. So we do not need to cut a big piece of signal here at all. Okay, next we compare the critical densities at which these narrow features appear in two different traps. As I showed to you, they appear in two cases, for the trapped magnons and for the bubble. And what we saw there, if we compare these critical densities, that for the cylindrical trap, we observe these at much lower densities, of the order of 10 to 17. For the bubbles, where we have higher density, we observe it at 10 to 18 or about that. So basically, we have more tight trap with larger spacing between the levels for the bubbles. But we see that we need higher density. This is in contradiction with the behavior observed for real atoms in trapping experiments with Bose-Einstein condensates. There it is vice versa. It would be like this, but we see it like this. So we need higher density for more tight trap, which is unusual. How this all can be explained? I need maybe 3-4 minutes. Do I have 3-4 minutes still?
It's high time to finish.
I'm finishing after a couple of minutes. How can we explain all of this? So this all looks like BEC-like behavior, accumulation at the ground state of these magnons of quasi-particles. But how quasi-particles can condense? We all know that the statistics of the BEC phenomenon is defined by this Bose equation, which looks like this. Here we have ground or any state energy. This is chemical potential, this is temperature. So basically, when the chemical potential reaches ground state, we have divergency here, and the ground state is accumulated. It is how it happens in real BEC. But quasi-particles, they are always in equilibrium, having zero chemical potential. So their occupation numbers, they are dictated by the temperature. So in principle, for equilibrium system of quasi-particles, like photons, like phonons, like magnons, one cannot get BEC. It's impossible. But if we have non-equilibrium situation, when we are continuously pumping magnons into the system, so that their populations, occupation numbers, they are non-equilibrium, then it turns out that they may get accumulated at the ground state. And this phenomenon was predicted by Herbert Fröhlich very early in 1968, and it was predicted for the branch of modes in the coupled oscillators. And he said and predicted and described in this paper that it may happen even in biological systems, in large molecules, in a rather wide range of systems. What happens in our case? In our case, we have chemical potential which can be derived by this expression. Here is the Magnon pumping rate. This is the energy of the ground state. And it turns out that the energy of the ground state via the effective mass, which I showed before, is inversely proportional to the square root of the hydrogen density. So if we put this here, and remember that the pumping rate is also proportional to the density, we obtain that our chemical potential does not depend on hydrogen density. But the ground state energy depends as inverse square root here from this equation. So if we plot chemical potential, which is constant, with respect to hydrogen density, and the energies of ground states of the spherical and cylindrical traps, at some point they cross each other. It means that our ground state energy is equal to chemical potential. So basically here we have divergency. So we get strong occupation of the ground state. And we get this VEC phenomenon. Therefore, and it turns out that the ground state energy for the spherical trap is higher than for cylindrical. Therefore, we get such dependence that this density, critical density, is higher for the spherical trap. Here are my conclusions, and basically I don't have time to read them. Details can be found in these papers. Thank you.
Thank you very much for your excellent lecture, and now we can ask you maybe, have you any questions?
Here is a question.
Thank you for your presentation. It was very exciting. I have two questions, if you don't mind. First of all, on slide 1, you have a super leak. I have a question. As I know, in superfluid, you always have two coexistent motions, in forward direction and in transverse one. And how do it?
Well, can you get out of the? Yeah, that's slow. I just wanted to jump there. Yes, when you hit superfluid, there are two motions, normal and superfluid component. Superfluid goes towards the heater, and normal component goes back.
But in a superfluid state, you have two motions there, no, in forward direction and in reverse, it's so-called superfluid. And how does this super leak works? So here we have the plug or super leak, which is transparent only for superfluid component. So when we heat here, it doesn't allow the motion of normal component. So the superfluid goes in, but the normal here cannot go back. That's why the amount of helium and pressure here increases. Oh, I guess. And another one, you've said that your bubble is around micrometers, something like this. Is it possible to observe it visually or something?
We see it by the change of capacitor, not maybe to the smallest size, not to 20 micrometers. We may probably resolve 50 micrometers, the smallest. So we still see that this frequency of this oscillator where this capacitor is connected, it's still changing down to this 50 micrometer. But of course we don't have any visual contact here or any. But
you have a very large density of your particles in this bubble, so I guess it would be possible to observe it by light or something.
Yeah, but here, in principle, it's correct if we would be able to build here some light guide and then may look for some transmission. But think, what kind of optics would you use for atomic hydrogen? In ground state, electronic state.
Yeah, I guess it's really hard.
It's Lyman alpha, the smallest, and the frequency is 121 nanometer. So it's vacuum UV. There are no lasers in this region.
Yeah.
So that's why it's extremely difficult to work with hydrogen, and that's why the game of the race for the BEC was lost by hydrogen researchers with respect to other alkali vapors. Because with other alkalis, you can use visible optics for detection. But with hydrogen, because of the very large energies, electronic energies, you need very strong energy of the light, very low wavelength, high frequency. So simply such lasers do not exist.
Any more questions? I have one. Please show the first slide. Not first, but one of first. This. Oh yes.
This one.
The previous. Yes.
Yeah.
Yes. You use classical equations for spin diffusion and in the following, yes, but here we use the notion of the precession for the single spin. Is it for simplicity or?
Well, this is for simplicity, of course. This is for simplicity. It's actually the solution of all this stuff can be found. It's transport properties, this paper, 1, and then there is 2 and 3, they are one after another. So it's 100 pages. People were calculating full quantum mechanical calculation, calculating these collision integrals and everything. And finally they come to the equation which is more complicated than this.
Yeah,
but I simplified it for small deviation, small magnetization. For large mu, it can be modified to this more or less tractable form, so that we can see really that there is a kinetic-like term, like in Schrödinger equation, and potential term. And it can be then just described how does it behave.
We use a very diluted spin system, yes, but it is necessary to consider this community of all spins, yes, and we can use macroscopic description for this event, yes?
Yeah, but here we consider only pair collision. That's why we don't need to consider any other particles. We have only 2 atoms. But of course, then these collisions must be averaged, because there are many of them. And that leads to, of course, all these collision integrals calculations. And so depending on the distribution of energies, velocities. But basically in one event, it's just 2 atoms.
Too complicated. Okay. Any more questions? No? Thank you again.